Hello, this is Mr. Miller. Welcome to video 5D. This video is about Rolle's theorem. Rolle's theorem, we just got to know what it says and how to apply it. Okay, it's kind of a theoretical result, and it's used in proving other theorems. Rolle's theorem has three conditions. First of all, f has to be a continuous function on a closed interval. It has to be differentiable in between the endpoints, and at the endpoints, the function has to be equal. So we see that here. Here are two examples of functions that meet that. This kind of pink function is continuous, it's differentiable, its derivative exists everywhere in between the endpoints, and the value of the function is equal at the endpoints. It has the same y value. Here's another example. Continuous function, differentiable, and the endpoints, the y values are equal to each other. Okay, now if that's true, Rolle's theorem says there's at least one point in the interval where the derivative is zero. There might be more than one, but there's at least one. So right here we see this point the derivative is zero, and right here the derivative is zero also. Here at the two red dots, the derivative is zero. Okay, so Rolle's theorem is true in those two cases. Now, generally, we have to check that the conditions apply and find the points that make Rolle's theorem true, where the derivative is zero. Okay, so here we have a function. It's a cubic function on the interval -1 to 2. Polynomial functions are continuous, and their derivatives exist. They're very nice. And we have a graph here. We could check this on our own, but we see that the endpoints have the same y value. Okay. So all the conditions for Rolle's theorem are true. Rolle's theorem guarantees that there's at least one point where the derivative is zero. In this case, there are two. Let's find them. So we're just going to find y prime and set it equal to zero. So we get minus 3x squared plus 4x plus 1 is equal to 0. Okay. And we can use the quadratic formula to find out what values make that true. So we get x is negative b plus or minus the square root of b squared, which would be 16, minus 4 times -3 times 1 would be plus 12, all divided by -6. So we get x is -4 plus or minus the square root of 28 over -6. And if we evaluate this, we get approximately x equals -0.21 and x equals 2.54. Sorry, 1.54. Yeah, 1.54. Sorry about that. The x equals -0.21 would be that point right there where the derivative is 0. And apparently 1.54 would be this point. Okay, let's take a look at another example here. It's a little bit more difficult function, but it satisfies Rolle's theorem. This function is continuous in between -3 and 3 and differentiable. And at the endpoints, it looks like it's equal to 0. Okay, so Rolle's theorem guarantees that there's at least one place where the derivative is 0. Looks like it's somewhere around here. Okay, so let's try this out. We need to take a derivative. So for this one, we need the quotient rule. So it would be g f prime minus f g prime over g squared. So this would be -x plus 4 for the derivative times f prime minus f times g prime all over g squared. And this would be y prime. So if I simplify, I get -2x squared plus 8x. And this minus times a -1 is really a +1. So we're going to end up with plus x squared minus 9 all over minus x plus 4 squared. And if we keep simplifying, we get minus x squared plus 8x minus 9 all over this. Okay, and we're interested in where this is equal to 0. Well, in order for a fraction to be 0, the numerator has to be 0. So we're going to set negative x squared plus 8x minus 9 equal to 0. I'm going to divide by a negative 1 because I don't like that too much in the leading coefficient. So we get this, and, well, time for the quadratic formula. So we get x equals negative b plus or minus the square root of b squared, that'd be 64, minus 4 times 1 times 9 would be minus 36, all over 2, which would equal 8 plus or minus square root of, all right, a lot of mental math here, 5828 over 2, and let's find the decimal for that. Okay, when I did that in my calculator, we get two values. We get x equals 1.35, and we get x equals 6.64. Now 6.64 is not in our interval. The value that's in our interval where the derivative is 0 is 1.35, which is right here. Looks like it's in between 0 and 2. 1.35 kind of makes sense. Alright, so Rolle's theorem is actually not hard. What's hard is taking the derivative and setting it equal to 0. Alright, now here's a trig function. We don't do these often enough, so this will give us a little practice. Cosine function is continuous and it has a derivative everywhere. And at the endpoints, the value of this function is equal to each other. Alright, so we want to take the derivative. So we get y prime equals minus, well, the derivative of cosine is minus the sine. So we get minus the sine of 2x times the derivative of the inside function times 2. So y prime would end up being 2 sine of 2x. Rolle's theorem says that this should be 0 at least once in the interval. So we're going to set it equal to 0 and try to solve it. So we get, if we divide by 2, we get sine of 2x equals 0. We can use a unit circle to try to solve this, but I want to talk about what happens if you use your graphing calculator to solve this. You can certainly put this in the graphing calculator, and when I do, I get something that looks a little strange at first. I actually get a weird symbol. I get an at symbol in 13. I think you'll get the at symbol and n and maybe a different number, pi over 2. Now, this is one really goofy symbol here. You should interpret this as just some number n times pi over 2. It's all the multiples of pi over 2. So it's n pi over 2 for n equals 0, plus or minus 1, plus or minus 2, etc. There's actually an infinite number of values that make this equal to 0. But we only want the ones in between negative pi and pi. So I'm going to start putting in values of n. We're only going to keep the ones in between negative pi and pi. So when I let n equal 0, 0 times pi over 2 is 0. We get x equals 0. Alright, when n equals 1, we get x equals 1 times pi over 2. Okay? When we let n equal 2, we get x equals 2 times pi over 2, which is pi. That's already at the endpoint. We're looking for values inside the interval. If I start going the other way, letting n equal negative 1, we get negative pi over 2. That's fine. And if I let n equal negative 2, I get negative 2 times pi over 2, which is negative pi, which is the other endpoint. So we get this weird expression. We got to think of this expression here as just n, or just some variable times pi over 2. It means the multiples of pi over 2. And we start picking out which multiples work in our interval. Anyway, so there are three values. Negative pi over 2 is this one, 0 is this one, and pi over 2 is that one. There were 3 places where the derivative is 0. Okay, here's another type of example. This one we're not going to have to do a lot of work because it turns out Rolle's theorem does not apply. This function is continuous, so this part is true. Sure, it's continuous, but it doesn't have a derivative here. It's a sharp corner. The tangent line doesn't exist there, so it's not differentiable. So Rolle's theorem does not apply. Okay, so we can't conclude anything using Rolle's theorem. So if it has a cusp or a corner, we can't go any further. All right, here's our final example. Okay, so we have this nice, beautiful cubic function. It's equal on the endpoints. So the value of the function is equal at -1 and at 4. It's continuous and differentiable. We just got to do it. So y prime equals 3x squared minus 8x minus 1. And we want to set that equal to 0. Okay, I don't see a way of factoring it, so I'm going to go for the quadratic formula. It would be a plus or minus the square root of b squared minus 4ac would be plus 12 all over 2a. That would be 6. And I get x equals 8 plus or minus the square root of 76 over 6. And if we find the decimals for that, we get x equals negative 0.12 and x equals 2.78. Both are in their interval. We found that point and this point. Those are the points we found. So 2 points make Rolle's theorem true. Okay, now we did some non-trivial examples. Polynomials are pretty easy to differentiate, but trig functions and rational functions can be difficult, but we can muscle through it. All right, well, you can also use your calculator to find the derivative, by the way, and that can make it easier. So we have 3 functions here for your journal assignment, and actually Rolle's theorem applies to each of them. These are polynomial functions. They're nice. This function, the last one, has an asymptote at -4, but that's not in our interval. All right, so you should show that Rolle's theorem applies and find where the derivative is 0 in the given interval. Okay, good luck.